Welcome everyone. This is experiment number 3. Okay, as you know, like we did the first 2 experiments in the last 2 weeks. So in experiment 3, we're going to deal with magnetic circuit. Okay, we already covered this in the lecture class, isn't it? We had last week 2-3 lectures on this. So today we'll do the same thing what we learned in the lecture class in the lab. Okay, so we'll try to find the characteristics of the magnetic circuit. So you can see the name magnetic circuit characteristics. So what is characteristics? Characteristics means the behavior or the information or something which gives the the characteristics of a particular circuit. So if we say the characteristics of a magnetic circuit, who are they? They are actually few parameters. For example, magnetic field intensity. Okay, intensity we denote by H. This is one of the characteristics, right, of the magnetic. So if you know the intensity, you know how the magnetic circuit is, right? So this is one of the characteristics. You understand? Similarly, density, which is denoted by B. This is another characteristics, right? So that means how the flux lines are put on the magnetic core. Are they dense or not dense? Okay. Third one is permeability. So permeability is denoted by mu. So this is how easily the magnetic flux lines can establish in a core. This is the permeability, right? And the fourth one is the reluctance. Reluctance, which is denoted by R. This is another characteristics, right? So that means this is the opposite force to establish the magnetic field. So these are the 4 characteristics of a magnetic circuit, right? Can you tell me what is the characteristics or what are the characteristics of an electrical circuit? Voltage, current, impedance, right? Yes. These are the characteristics of an electrical circuit or electrical network, right? That means if you know the value of voltage and current, you can see you can understand its behavior, like how much is the power, how much is the reactive power, and so on. So similarly, these are the characteristics of the magnetic circuit. So we will try to find these characteristics by doing the experiment today, right? So how to do the experiment? I already explained several times in the lecture class that how we make the magnetic circuit. To make the magnetic circuit, we need first of all what? A magnetic core, isn't it? Yes. To make the magnetic circuit, we need a magnetic core. This is the first thing, right? And we own the coil in one of the sides of the core. So this side will put the coils and the winding, right? And then we will apply the voltage V, for example. Okay, because of this V, I will start flowing, and this I, whenever it flows inside the coil, okay, this I is flowing. If I flows, a flux establishes here, which is phi, and this makes the magnetic circuit, isn't it? This is how we make the magnetic circuit. So exactly the same way we will make the magnetic circuit in today's lab. So can you see the magnetic core we have in our hand? So this is very heavy, by the way. So this is the magnetic core. Let me take this to show you. Okay, this is the magnetic core. Can you see it is looking exactly similar like what I have drawn here, isn't it? Yes. You see, this is the core, the black shape, and in one side of the core we have the coil. Okay, can you see the coil? So these are the coils, right? So these coils, if you put in one side of the core and you connect the voltage in these 2 buttons, the current will flow through the coil and the magnetic flux line will establish here. And if you increase the voltage, the magnetic field will increase. And after some time, you will listen a sound. You see like the sound of shivering something. If something is shivering like this, for example, if you put your mobile phone on the table and it starts vibrating, what happens? It listen a sound, right? Yes. Because it is vibrating. Similarly, if you apply the magnetic field here, because of the magnetic flux lines, you will, whenever we'll do the experiment, you will listen a sound because of the magnetic field and the flux lines. Okay, we'll do that later, inshallah. Now, coming back to our work. So how we will do the experiment? You see, we turn on the voltage source, we apply the voltage, and we measure the value of voltage and current. Now the biggest question is that how to get these parameters H, B, mu and R. Do you think that the Casilab can give us the parameters directly? Can Casilab measure B, H, reluctance? It cannot measure these parameters directly, because we did the experiments last 2 weeks. We saw that the Casilab provides us what? Voltage and current, isn't it?
Yes, yes.
So it gives us voltage and current, but we know some formulas, some relation which links the voltage and current with H. For example, what formula we know for H? We know that H equals to Ni divided by Lc. Can you remember this formula?
Right.
Who is N? N is the number of turns, right? So for this magnetic core, the number of turn N equals to 250. Okay? And Lc is the mean length. I will show you what is the mean length of this core. So we'll get a value of mean length Lc. So you see, if you put the value of N and Lc, and this I is taken from the Casilab, right? Thus you can get the value of H. You understand what I am saying?
Yes.
Are you getting me, guys? So that means this value of H, B, mu and R, all of them we will calculate. We will calculate, but we will measure actually the value of voltage and current. You understand this? So that means, whenever we'll do the data taking, we'll have voltage, we'll have current. Okay? So for example, we'll take the number of data 1, 2, 3 up to 10 or 11, whatever. Okay? So this voltage and current we will measure, but this H, B, mu, reluctance R, all of them we will calculate. Okay, calculate. And these two we will get from the Casilab. So we'll get from the Casilab. Clear? So and by pressing F9, we will increase the voltage and we'll get the value of voltage and current and this. So these formulas are provided to you in the lab manual. So if you see the lab manual carefully, like these formulas are written to you. All of the formulas are given to you. So they are very easy formula. I can just write down very quickly. Like the formula for H is this one, Ni divided by Lc, right? Here I is from the Casilab, N and Lc is provided to you. Okay? What is the formula for B? Let me write the formula for B. This is the formula for B. B equals to V divided by 2 pi F An. This is the formula. Actually, this formula is coming from some basic formulas we have already discussed in the lecture class. I can give you detail later. Okay? So 2 pi is 3.1416. F frequency. What is the frequency? 60 hertz. Right? A is the area. Remember A? The cross-sectional area, right? So how to measure the cross-sectional area? We will see, like the length and the width, if you multiply, you will get the cross-sectional area. So the area also we will calculate. Okay, they are constant. N is the number of turn. So you see, if you know the value of B, you can get B, right?
Yes.
Are you with me?
Yes.
Okay, so if you get the value of B from the Casilab, you can get B. Similarly, what is the formula for mu or the mu R? The formula for mu R is E Lc divided by 2 pi F N square A mu naught into I. Try to understand. This is not E, by the way. It's written here E. This should be V. So this V is voltage from the Casilab. I is current from the Casilab. And the remaining everything are constant. Can you see? Mean length 2 pi F N number of turn, A area, mu naught is the constant parameter 4 pi into 10 to the power minus 7, isn't it?
Yes.
So if you know the value of V and I from the Casilab, you can get the value of mu. Clear?
Yes.
So the last one is the reluctance. The formula for the reluctance is omega n square I divided by V. Again, see, omega is 2 pi F, n is the number of turn, constant, Only V and I, if you know, you can calculate the values. Clear? So this is how we will calculate the magnetic circuit characteristics through electrical circuit parameters. I am repeating this statement again because this is the most important thing of this today's experiment, that we'll calculate the magnetic circuit characteristics through electrical circuit parameters. Who are the electrical circuit parameters? Voltage and the current. That's it. Clear? This is what we'll do. And for that we need to know these parameters. N is the number of turns. It is written here. How much? 250 is written already. 215 is written over here. LC is the mean length. Can you remember how to calculate the mean length? You see, this is the core. Mean length is from corner to corner, right? From the center to center, not from the corner to corner. Sorry, center to center. So if you take a scale, measuring a scale, this is centimeter. Okay, we just put here. You see, this is around 12. Sorry, not 12, 11. So this corner to this corner is 11. So how many sides it has? 4 sides. So what is the LC? 4 into 11 centimeter, right? Which is 44 centimeter. Clear?
Yes.
So this is 44, sorry. This is 44 centimeter, that means 0.44 meter. F equals to 60 hertz. A equals to what? Let me measure A. A is the area, so length is 3.8 and width is also, I think, 3.8. Yeah, 3.8. So it should be 3.8 multiply 3.8 centimeter square. Are you with me?
Yes.
So this is the area. So if you multiply, and if you need to convert it into meter square, okay, by dividing by 100. So this is how everything, all the parameters will calculate. Is there any question? Any question? No. So the last thing is that in the report, they will ask us to plot some curves. Actually, in the report portion, they will ask us to plot 4 curves. So one is B versus H. Another is V versus I. Another is mu R versus H. And the last one is reluctance versus H. You understand? These 4 curves you have to plot and you have to provide in the report. Okay? Any idea how can we plot these curves? It's very simple. Why? Because whenever you get all the data, you just go to the display option of the Casilla, you select x-axis and y-axis. That's it. Clear? If you select x-axis and y-axis, you will get the curve, right? So you will get the curve like all of them in the Casilla. Okay? Here I just want to mention one thing. Can you remember how BH curve looks like? BH curve. Yes, it increases, then it goes to saturation. Remember? We discussed in the lecture class. The name of the BH curve is magnetization curve. So it always look like this. It increases and it goes to saturation. Can you remember, guys?
Yeah.
Like this BH curve looks like this. So here, one interesting thing is that, can you see? N is a constant, right?
Yes.
LC is a constant. So can you say that H is directly proportional to I? Can you say this N is constant, LC is constant? So of course H is directly proportional to I, right?
Yes.
Are you with me? Okay. And from here you see 2 pi f a n. Everyone is constant, right?
Yes.
So that means from here you can write B is directly proportional to V. So that means B is proportional to V, which is voltage, and H, intensity, is proportional to I, right? Now come to the curve. This one is proportional to this one. This one is proportional to this one. So if this curve look like this, how this curve will look like? Any idea? It will look like same, right?
Yes.
Because they are proportional, Maybe the values are different, but they will look exactly same. So you see, voltage versus current curve will be similar like this. You understand? Is this the normal case or the special case? Is this the normal case or the special case? Like voltage versus current curve. Should it look like this? Just think about it, guys. Ohm's law. What we started in the Ohm's law. In the Ohm's law, we started that the I, voltage versus current, this is our R, right?
Yes.
V equals to IR. So that means, you know, if you plot the curve, you will always get a straight line, isn't it?
Yeah.
So actually, Ohm's law says us that the voltage versus current curve should look like this, a straight line, isn't it?
Yes.
But whenever you apply this in the magnetic circuit, it doesn't look like this. It cannot go to the, you know, it cannot follow the linear curve. Rather, it follows the linear curve for some time and then it goes to saturation. So this is a special case. So in the report, they will ask you that YVH and VI curve look similar. You understand? So you have to explain these things and you have to explain these equations and so on to show that why they are looking similar. They are looking similar because of this and this relationship. Clear, guys? So this is the summary of today's experiment. So it will be an easy experiment. We'll just connect the circuit. It's a very easy circuit and we'll do the Castle-Lab setup. But you know, the conception is a bit deep. You have to understand what's going on. So we'll make the circuit, we'll apply the voltage and current, and we'll put an ammeter here in the Castle-Lab and a voltmeter here in the Castle-Lab. This ammeter and voltmeter will give us the voltage and current. This voltage and current. So we'll give it from the Castle-Lab. And the remaining things are all we have to calculate by formula. How many formulas? 4 formulas I have written. This is formula number 1 to calculate H. Formula number 2 to calculate B. Formula number 3 to calculate mu. And this is formula number 4 to calculate R. Okay? You have to put all of them, and after getting all the values, you have to calculate, you have to draw these 4 curves. Curve number 1, 2, 3, and 4. So all of them you need to put in the report to write a complete good report. Clear, guys? Any question? Okay, guys. So this is the connection. This is the connection diagram for our today's experiment. So as you can see that in today's experiment we are using the magnetic core to make the magnetic circuit, and this magnetic core is having the winding in one of the sides, and the number of turn is provided here, which is 250. So if I just turn it back, you can see the coils very clearly over here. Like we have some insulated coils inside, and this is winded in one of the sides of the core to generate the magnetic field. And if you look carefully the connection, this is very simple connection. It's much simpler than the weeks before. We have just one source, which is line 1 to neutral, which is single phase AC. Can you see? This is our single phase AC source, line 1 to neutral, and it is connected to the core, magnetic core. So you can see it is coming to the magnetic core through the Castle-Lab. So you see, this is the Castle-Lab part. So this is the Castle-Lab portion we are using. We are actually using 2 channels today. This is channel number A, which is measuring the voltage, this voltage, okay? And the second one is channel number B. This is measuring the current, which is the current which is flowing through the coil. Okay, so these 2 things will measure from here, and on the measurement data we'll apply some formula to calculate the remaining parameters. So this is all about the connection. So we will do the Castle-Lab setup now, and then we'll take the data. Do the Castle-Lab part. Okay, we're turning on the Castle-Lab. It's asking for the, okay, just. So 2 channels we're using today. I will do it a bit quicker because I showed you very slowly in the last 2 weeks. So channel A and B, right? Yes. You just click here. This is channel A. It's activated. You select the manual recording and select here RMS value. Why RMS?
AC.
Because our supply is AC. Done. Second one is channel number B. You click, it is activated, and this is RMS value, right?
Yeah.
Okay. So now you close this one. You don't need that anymore. The second step is to define the parameters. So go to the calculator, click on the formula, new. So the first 2 things you have to define is voltage and current, right?
Yes.
Okay. So voltage, symbol is V, unit is volt from 0 to 100. Okay, what should be the formula for the voltage? The first one, right?
Yes.
So that means UA1, isn't it? Because the name of the channel A is UA1. Here it is written,
Yes.
right? Why you need to multiply with 100? Because over there you're supposed to divide by 100. Did you? Yes, you have to divide, and here it should be 1. Okay, so for the voltage we divide by 100 there. So that's why you need to multiply with 100 here. Clear? Okay, so the next one, new current, right? Current symbol is I, unit is ampere, from 0 to 10, for example, decimal plus 4. What should be the formula? UB1, right?
Yeah.
So the next one, the name is UB1. So that's it only. Okay, you don't need to multiply with 100. So done. So these two things we have already got. You can see over here it appeared. Voltage and current, right? So you go to the display. Standard displays, you know, they have already UA1, you don't want to see, you just delete. UB1, you just delete. So the two things you have here, voltage and current, you see? Now how many parameters you need to see more? 4 more parameters, remember? H, B, mu R, and reluctance R.
Yes.
So these 4 parameters you need to see. So that's why you need to define them one by one, right? So we open a new quantity, and the name is intensity. H is what? Intensity, right? So what is the symbol?
H.
H. Unit ampere turn per meter, right?
Yeah.
So from 0 to 100 anything. What is the formula? Can you see? The formula for H is what? Ni divided by LC, right? So here, who is N? Number of turns, right? How much is the value? 250, right? So instead of N, you just write 250. Clear?
Clear.
Multiply with I. I is there, I. So you just write I, because I is already there. You see this I is already here. So you just write I divided by LC. How much is the value of LC? So 44 centimeter, it should be 0.44 meter, right? So this is your H. You see H is here now. The next one is B. What is the name of B? Density. Density. Symbol is B. Unit is Tesla. And what is the formula? Can you see this one? Do you have pen? Anyone? So this one, just try to see here. Like the equation is this one. So it will be B equals to E divided by omega is what? 2 pi F, right? 2 pi F N A. Okay? So E is the voltage, we know. 2 pi 3.14. F is the frequency 60 Hertz. N is the number of turns, and A is the area. Okay? We just put the values over here now. So E, what is the symbol of E? There V, right? So you just write V divided by, everything is in the bottom, right? In the denominator. So you just have to put the bracket. You understand? Yes. So 2 multiply with 3.14 multiply with 60 Hertz, 60 multiply with N, 250 multiply with A. Can you tell me what is the A? Abdurrahman, can you check what is the value of A?
44.
A. 3.8 multiply 3.8, right?
14.44.
14.
14.44.
So it should be 0.001444. Isn't? Am I correct? Because you have to divide by 100 and divide by 100 also, right? To convert into meter square. So this is the formula. Okay? So you see B is here now. Can you see B is here? So the H is defined, B is defined. So the next one, open a new quantity. What is the next one? Mu R. Right? This is the mu R. Okay. So mu R is permeability. permeability. Symbol is mu. So let's give it U. Okay, U. What is the unit of permeability? Is it written here? No, okay, we can escape this one. Okay, so let's see the formula. What is the formula? E, which is V, multiply with LC. LC was how much? 44?
Yeah.
44. So 0.44. So give it as a bracket. Give it as a bracket. And then divide and start a new first bracket. You understand?
Yeah.
Because the formula, you have denominator two terms, sorry, numerator two terms. It should be in the bracket. Then give us backslash, that is actually divided by, and in the denominator you have 4 terms or 5 terms. So they should be all together in the bracket as well. So this is omega. Omega is again 2 multiply with 3.14 multiply with 60. So this is our omega multiply with n square. So you cannot put a square, so it should be 250 multiply with 250. Are you with me?
Yes.
Okay. So multiply A. How much was the A? A was 0.001444, right?
Yes.
Multiply with mu 0. Okay. Mu 0 is 4
Pi.
into pi. Pi was
But how I put the
3.14. I cannot exactly remember what we did last time. Into 10 to the power minus 7, right?
Yeah. So 6 zeros will.
I think let's give a try. So 10, let's give a try. 10 to the power. If it doesn't work, it will show error. You understand?
Yeah.
Okay, let's give a try. Let me put it at the last, so that. Okay. What else is remaining? I. So you just write I over here. Okay. Let's see. If I click here, if it is fine. Yeah, it's fine. So if it is not fine, it will give you an error sign.
Yeah.
You understand? And it will not appear here. So that means the formula I have written is correct. Okay. So now the last one is reluctance, right?
Yeah. And
Reluctance. Okay. So reluctance, symbol is R, unit is ampere turn per Weber. Ampere turn divided by Weber. So what is the formula? Omega. So that means 2 into 3.14 into 60. Is it difficult? It's not difficult at all, right? You just see the formula and write there. That's it. Okay? So
60.
into n square.
60.
Yeah, I've written 60. Into n square. So 250 multiply 250 multiply I. I. So divided by E. So divided by E is V here, right? So you see R is here. So can you see the formulas now?
Yes.
Can you see the formulas? See carefully. This is our V. This is our I. These two we will measure by the Casilab. And the remaining 4, field intensity H, density B, permeability mu, reluctance R, we have just written the formulas as it is, we have seen in the lecture slide and also in the manual. Clear, is it? Is it clear? Okay. You can close the video, I think. Now, taking the data now, we have done the connection and the Casilab setup. So before taking the data, just few things you need to be careful. One is that the source is in the 0 position, is 0, and you are taking line 1 to neutral. So this button should be line 1 to neutral, right? So if it is in any other location, you will get wrong data. Clear? And the third thing is that your the current screen for the current, the ammeter should be in front of your eyes, so that if anything wrong, you can just immediately see it and you can turn off the source. So we'll now increase the voltage source slowly and we'll take the data. Okay. So first data we'll take at 0 volt. Press F9. So it's almost 0. So we'll apply initially some small value, 15 volt, F9, 30 volt, F9, maybe 45, F9, 60 volt, F9, 70 volt, F9, 80 volt, F9. Now before going further, you can listen the sound, I think, right?
Yes.
This sound is because of the generation of the magnetic flux around the core, and as because it is generating some good amount of flux, so it is actually shivering the table as well. So we'll increase the voltage more, 90, F9, 100, F9, will reach up to 120, 110, F9, 120, F9. So two things. One is that the data table is ready for us. Can you see the data? All the data here, like the value for the voltages, currents, H, B, mu, R, all the data are ready. So if you want to plot anything, it's very easy. You just go to the display, we'll plot that. Okay? And this is manual recording, so that's why we have taken 11 data. You can see n equals to 0 to 11. But the interesting thing is that the sound. You can hear a good amount of sound now. This sound is actually coming from, it is as because the core is on the table, and because of the magnetic field, it is actually shivering. Okay? And this is creating the sound. But still, you can touch the core. There is no harm. Why? Because there is no current in the core. Isn't it? Is there any current in the core? Where is the current? Where is the current? Current is in the coil. You see, current is here. You see how much current is flowing? 0.47 ampere of current, which is a good amount. If you just touch that current, you should get shock. But if you touch it, the flux, like touch the core, nothing happens to you because there is no current here.
Yeah.
Okay? It's only the magnetic flux. Yes. What is? Now collected all the datas. Okay, 11 set of datas we have collected. Maybe you have seen here, like 11 set of datas we have to calculate the value of voltage, current, reluctance, and so on. So the last step is to see the curves now. Okay, so in the lab manual they asked us to plot 4 curves: voltage versus current, B versus H, mu versus H, and reluctance versus H. Okay, so one by one we will just plot the curves, and I will show you the curves here. So I have gone to the display option, click on the new. Okay, it opened a new window, add new curve. So in the x-axis, you put H, and the y-axis you put B. So it is having only H versus B, you see? So nothing is here. You go to the maximum minimum and maximum minimum. Can you see the curve? Is it matching with the theoretical idea?
Yes.
Exactly, right? Because this is how it should be, B versus H. So the next one is, instead of H, it should be I, and instead of B, it should be V, isn't it?
Yes.
Because I said B is directly proportional to voltage, and H is directly proportional to I. So they should be again similar, isn't it? Can you see the curve?
Similar.
Voltage versus current. So this is voltage versus current. It should be a straight line according to the Ohm's law, but here we are getting some saturation. This is the second curve. The third curve, I think this is mu, in the x-axis it should be H, and the y-axis should be mu. So find maximum minimum, find maximum minimum. Yes, this is the curve. Okay, so it will go here, reach a saturation, then fall down. You can see in the textbook that it should look like this. And the last one, instead of mu, it should be reluctance. Okay, so I have just taken the maximum minimum. You see the curve should look like this.
Yes.
So these are the 4 curves. Okay, so we will, this is the last thing I need to show you. So you can just take the picture now. Okay, thank you.